Good evening. I think we can start our session. It's 8 p.m. Eastern time, of course. Hello. Okay, that's what we have. We have the second section in this week, in this lesson, 2.9, linear approximations and differentials. Tonight, I will try to talk about the linear approximation, and if we will have enough time, I will talk about the differentials. If not, we can finish the session, of course, around 9 p.m. and I will add a short video about the differentials. Okay, that's when you can check tomorrow morning. But definitely linear approximation. Okay, that's when we will learn how we can use a line and actually a tangent line to approximate a value of a function. Okay, and of course, like normally we will probably not do this, because why we have to approximate the value if we can actually get the actual value, but like the actual number. But sometimes it is helpful, like for example, when we have let's even say not really complicated function like square root of x. Okay, and then we would like to find, out maybe 4.01. Okay, that's mean what is the square root of 4.01? We can approximate, but the idea is instead of using the root function, we may actually draw a tangent line. Okay, you can see. And we know actually a little bit wrong. I will draw another one at 4 actually, because that's the idea. Okay, I can draw a tangent line at 4 because 4 is a good number for the square root function. And instead of using the actual function, I can actually use the tangent line, because we know that the tangent line it's almost the same like the curve. Okay, that's the main idea, that instead of taking a function, we will take a line, because line is always nice and straightforward equation, mx plus b. And we can substitute whatever value for x. Of course, the slope and the b value, the y-intercept, we can get easily, and we can compute the corresponding y value. But having a square root function, or maybe trigonometric function, or maybe logarithmic function, sometimes it's not convenient and not helpful to have all of these functions. Okay, that means instead of like some functions, like instead of any function, we will try to approximate with the line, but of course the tangent line. Okay, that's me. Let's see how we can do this. Okay, because again, I'm trying to squeeze the entire section in one slide. Okay, that means we will look at this approximation, and we may nicely see, okay, this is the curve and that's the tangent line. And when we will zoom in, when we will go really close to the point of the tangency, a, f of a, we can see it's almost no difference. That means instead of taking a function, like I just said, we can just take the line. And line is always, yeah, just the multiplication, addition, subtraction in terms of calculation. Line is just the line. Simple linear form. But f of x, as mentioned before, could be complicated function. And again, I will probably repeat, but we may always use the calculator, or we may always ask computer to calculate like the square root of 4.01, for example. But the point is, when you will make some maybe coding, some programming, sometimes the whole model will not really like different types of function. Yeah, like as I said, trigonometric, logarithmic, exponential, even the root function. Okay? And then what you can do, you can remove the function, the original function, and you can put the tangent line. And you can say, oh, close to that point, oh, close to the point A, oh, my writing is funny. Doesn't matter, we can see, doesn't really matter if I use the complicated curve or if I use the tangent line. Okay, that's the idea, to have the approximation, linear approximation. Okay, and this is the picture that I will try to convince you even more that when we will take the curve and if we will zoom in, okay, you may look at the scale from 0 to 2, from half to 1.5, from 0.9 to 1.1. That means I'm really getting close to the 0.11, and any curve, doesn't really matter how wavy, how curvy is the function, it will always become like a line, yeah, like a tangent line. That means one more final statement, instead of a function, we will take a tangent line, okay, to approximate, to compare, to evaluate the values. Okay. Okay, the same information. Of course, the line, it will be the tangent line. Okay, and you may probably see I use like a L of x. The label is L of x because we call this linear approximation. L comes from the linear. Okay, okay. That's now let's look at the equation. And linear approximation is just the tangent line. That means we probably know how to find the tangent line. Okay? To the if the function and the point is given, no problem. But we will start. Actually, I would like to, before I show you this, that means when we have, let's say, a function, okay, f of x, the function f of x, and at the point, yeah, like this one, the point of the tangency is a and f of a, because I don't want to scare you with the equation that looks, you know the equation, I just wrote a different way. Okay, and if I will ask you, which I think we have this question, like find the equation of the tangent line to the function f of x at the point a, f of a. Then what we will do, we will use the point slope form, point slope, because point is given, y minus y1, m, x minus x sub 1. But the value of the function, okay, is f of a, and x value, x coordinate is a. And slope, first question tonight, do you think you can tell me how can I define the slope of the tangent line? Do you remember the slope of the tangent line? It's just the derivative, f prime at a. Okay, that means this equation that I just wrote is basically the equation of the tangent line. Because, oh, hang on, f prime, okay, f prime at a, because it's the slope at the given, I mean the derivative at the given point. That means it's f prime at a, okay. Okay, that means this is the equation of the tangent line. The only thing that I will do, I will add to both sides the value of f of a, because it's subtraction. I will just isolate y. That means this will be f of a plus f prime at a, x minus a. That means now we have a nice form of the linear function, but this is nothing, it's nothing different. You can see, you will probably create this. This is just the tangent line. Okay, but we will keep this way, f of a plus f prime of a, x minus a, and you know where this comes from. And just one more thing, instead of y, I will put L of x, because I will use this tangent line, I will, instead of a function, okay, at the point A. That's the reason that this will be L of x, linearization. And that's the formula, okay? Which of course, again, we knew this formula. Let's see now, I can show you now. That means this is the formula that now, nothing, yes, nothing new. It's just the equation of the tangent line. And if you forgot that form, you may simply start with the point slope form, find the slope, you have the point, and get the equation of the line, tangent line. Okay, okay. And I think I'm trying to derive this formula just this way, but it's the same way. We can see slope is defined as a y minus y1, x minus x sub 1, just the difference in x, difference in y's, rise over run. And my point is a f of a. This is supposed to be just a. Slope, of course, is the derivative, and we just multiplying by x minus a and adding f of a. The same as this equation came from this one, which actually that slope formula is giving me point slope form. Yeah, it's also nice. Everything is connected. Okay, no more talking about formulas. Let's see one more slide. That means this is tangent line at a. Okay, that means now this is this tangent line, and as I said, tangent, we will approximate a function using the tangent line. And we call this approximation the linear approximation, or tangent line approximation, or just the linearization. Everything is of the function f at a. Okay, let me move. Do I have? Okay, that's mean, and this is the equation. Yeah, we can see L of x, f of a plus f prime at a, x minus a. And one more time, I can draw just function. I'm assuming that is complicated function, and I don't want to use this function. I would like to use, let's maybe draw, I would like to use a tangent line. Right? Because we can see at really close, f of a, really close to the point A, we have no difference. Of course, I will not use this approximation. I will not say, this is the equation, f of a plus f prime at a, x minus a. So I can say that L of x is the same like f of x, but near, okay, near a. We can see only like really close to a. I can't really use the approximation. For example, like I will pick another value b. We can see this is the value of the function. This is the value on the upper dot will be the value of the tangent line. The dots are not close to each other. But when I'm really close to the point A, everything is on. Like we can approximate. Okay, that means let's find some approximation. And that's actually the question that I start the session. Okay? Find the linearization of the function square root of x at 4. That means one more time. It's of course, it's relatively, I mean, it's theoretically new topic, but it's nothing new. It's a nice new terminology, linearization, but please remember, if you see this type of question, you have to just find a tangent line. Okay, that means linearization means equation of the tangent line. Okay, and what I type? I think I typed the new form just maybe to get used to, but you may just use the point slope form. We have point, we can find easily slope and get the equation, mx plus b form. Okay, but I have my linearization, f of a plus f prime at a, x minus a. And can you tell me what I will substitute for f of a? Or maybe we can start, f of a will be yes, of course. Because a is 4, f of a will be square root of 4. Thank you. That will be 2. This is 4. And who can tell me what can I put for f prime at a? Can you compute for me? And then done. Yeah, that's what we can see. It's quite easy topic. Linearization means the equation of the tangent line. Okay, f prime at a? It's, yes, okay, I think I typed this somewhere. First of all, we need the derivative of the square root of x, 1 over 2 square root of x, and instead of x, we have to substitute a, which is 4. Square root of 4, 2 times 2, 4. Josh said and Noah said the formula, but it's 1/4. 1/4. Okay, let's see. Oh, I think I typed additional. That's 4. That's square root of 4, square root of 4 in the formula. We know where this comes from. That's we have 2, 1/4, and 4. Okay. And this is, of course, it's still not the final form, because it would be nice if I will distribute 1/4 times x and 1/4 times -4, which this will give me -1 plus 2 is +1. And this will be 1/4. That means this actually, the second box, is the final form, because it's mx plus b, 1/4 x plus 1. Okay? But I just want to like this form. I can maybe remove the arrows. It's also helpful. Okay? That means this one is also a good form. Depends. If you will have multiple choice question, probably the last form I will expect. But as soon as we will take this equation and try to approximate some values, the blue box will be a little bit more helpful. But I can show you in a minute. Yeah, but of course, mx plus b is the nice form. Okay, that's the equation of the tangent line. And I think, oh, I don't have a graph. I thought that I have the graph. It means I can square root of x. That's what I was drawing. And then a tangent line at 4. Okay. Oh no, a little bit. Yes. And this is 1/4 x plus 1. Yeah, looks good. And we can see really close to that point. Doesn't matter if I take the square root of x or the blue curve, I mean the blue line, which is the tangent line. Okay? I can approximate. So now my next question is, use example 1 to approximate the number square root of 4.05. Okay, and that's another, that's the application of this, that's the real use of the linearization. So let me come back to this slide, and I can use different color, 4.05. Okay. And the red dot will represent the actual value. Oh, I pressed something, oh no. Oh, which I didn't draw. Yeah, we can see the red. Oh, I'm pressing. But the blue dot, okay, will be the value on the tangent line, which I'm not really drawing. Oh, why I can't draw it? Okay, that's, we can see the red dot is the exact value. That means the exact value, okay, is square root of 4.5. Do we know, we don't know how to approximate. Of course, we may use the calculator, okay? But what I can do, I will try to, we will get the real value also. Maybe I will even ask you to use the calculator, but let's approximate without the calculators. That means we can see I can use the linearization, okay? Which means I can use 1/4 x plus 1. And instead of x, I will substitute 4.5 because that's the x. Okay, Yeah, that's how this works. And computing 1/4 times 4.05 plus 1, I think we can do this without the calculator. We will get the value of the square root. Okay, let's go to the next, to this slide. That's the approximation. Instead of the square root of x, I'm taking a tangent line. And now instead of x, I'm substituting 4. But one thing, this linearization, this tangent line, 1/4 x plus 1 is the tangent line at 4. That means I can use this tangent line only to approximate the numbers close to 4, near 4, which 4.05 it is one of the numbers. Okay. Okay. Can we compute this? 4.05 divided by 4. What I did, I kind of like put zeros because I can add zeros, that's not a problem. And then I will have 4 divided by 4 is 1, and 500 divided by 4 is 125. I just did this way because of course no calculators. And plus 1 means I will have 2.0125. Yeah, we can see no calculators and good approximation. And before we will check, I think I even used the calculator and I got the real value. But do you think, can you tell me, is this number an overestimation or underestimation? It's over. Okay, thank you, Kevin. And do you know why this is overestimation? Why we overestimated? This is square root of x. And how can I do this? This will be square root of 4.1. Okay, this is 4.01, 0.5. I was trying to, because we do have lots of explanation. The curve is it's downwards. Okay, the line increases more than the line of the other function. The right to the right of 4 on the tangent line. Okay, I think yes. I think everybody is perfectly correct because we can see this is my tangent line. Yeah, that's the tangent line at 4. And this value is actually the blue dot. Okay, that means this value is 2.0125 is the value on the tangent line. And yes, like all of the explanations, the characteristic of the curve is right because the tangent line is above the curve. That means instead of taking the real value, which we will check, we actually got the value on the tangent line, which again, they are almost the same, but really like, yes, logically, theoretically, they are different. Yes, they are different, but they are so close. And I think I have the actual value using the calculators, 2.011246, 125. We can see it's almost the same. That means it's a good approximation. And as I said, in the normal real situation, we will just take the real value. Okay? But using, like in some mathematical models, some computation, programming, coding, you may use it will be so helpful, and you will like solve your problems using the line instead of the curve. Okay. And okay, I don't have the graph. I thought that I copied the graph from your textbook. Okay, Josh, it's a good question. Josh is asking, how do we know if we are close enough? Actually, we don't know. Of course, if I will ask you to approximate the square root of, let me actually write, which I think I have this question, square root of 7. Yeah, like what do you think? Which actually we can probably do this question. Like I will ask you, that's actually, I think, one of my questions. Like use the linearization to approximate square root of 7. That means, what do you think? The 7, where is 7? Yes, actually Kevin gave us the good, okay, this is square root of x, because of course we're talking about the function square root of x, and then we'll definitely like 4, and we definitely like 9, yeah, because that's the square root of 4, square root of 9, that's 4. Okay, and now I'm asking to approximate 5, 6, 5, 6, 7. I'm trying to, okay, 7, 5, 6, 7. That means, what do you think? Shall we use the same, okay, the tangent line, like which value, where, like, okay, 7 is closer to 4 or to 9? What do you think? Which tangent line will be better? 9. Okay, that's you can see we can decide. Like if we understand that we just need the tangent line, and of course, if the tangent line, like for example, that tangent line, I can use the blue color. Okay, I can maybe, we will get this value, the blue dot. It's quite, yeah, we have a difference between the blue dot and the actual value. That means it will be still probably good approximation, but since 9, it's closer. What color I can use? Maybe green. I can use the tangent line. Oh, okay, at 9, tangent line at 9, and then my approximation will be that darker green, which is so close to the lighter green with the actual value. And that we can see, we can decide like wherever we want to approximate what tangent line to use. That we will not use the blue one, we will use the green one. Actually, shall we do it? I don't know if I do have the slide, but we can even solve it here. So I mean, we would like to approximate using the linearization, okay? And the linearization is defined f of a plus f prime at a x minus a. I'm just, okay. And then my a, of course, is 9 in this case. Okay, that means if I will ask you to use the linearization to approximate square root of 7, we have to find out that value 9. Okay, but you can see it's not bad. Okay, get ready and give me all of these values. What is the value of the function at 9? F of 9, it's 3, thank you. And then f prime, derivative of the square root of x at 9. 1/6, thank you. And then x minus 9. Okay, that means this is the equation, and I will keep that form. I will not distribute because I can show you why. That means I am approximating square root of x using this equation, but only I can approximate for the numbers close to 9, which 7, yeah, that's the only option that we have. It's relatively close. Okay, that means square root of 7 will be equal to 3 plus 1/6 and then 7, substituting 7. Because can you see why I like this? This part, x minus a, x minus 9 in this case, is showing me the difference, like how far away I'm going from the point of the tangency. Just for a second, like, can you see this one? Like if we have, this is definitely the tangent line at 4, and approximating 4.05, I can put here 4.05 minus 4. That means I can see that I'm going 0.05 away units. Yeah, that means just the form is just, yeah, nice. Okay, let's come back. Okay, that's what is 7 minus 9 is, we can try to get the value. 7 minus 9 is -2, And then 1/6 times -2 will be -1/3. Am I right? I'm trying to -1/3. 3, I can, 3 minus -1/3 will be 2 2/3. 2.2. Actually, I can leave it like that, right? Because I think even on the weekly assignment, I think I'm leaving that form. But what's the decimal? 2.6? 666? I think. Yeah, 2.2/3 at the 6, yes. But I think we will keep, because since it's the nice fraction, I will keep this one. Do you think you can check on the calculator? Because I didn't. No, that's actually a really good question. Really good question, because you're trying to figure out how can I use it. Can somebody use the calculator and check square root of 7? And can you type it for me? I have my phone. Okay, that means this is the real value, right? Square root of 7, I am just 2.645. Okay, 75, I can, yeah. That's, we can see it's perfect, it's nice. But you can see that the dark green and the light green, it's the actual value, and the dark green is relative. Even my graph is quite, yes, quite good. Okay, that's the way to, yeah. That's, you can see no calculators, of course, just the numbers to check, and we can get square root of 7. Yeah, how clever we are. Okay, let's see what I have, but you will see this. I think I have this question. What about square root of 11? What number, what tangent line we will use? Square root of 11. I'm just trying to, I think we will use 9, right? 11 is quite, it's closer to 9 than 16, because the next number is 16, the good number, the nice number. Okay, that's okay. That means even square root of 11, we can still use this, yeah, this equation. Okay, I have another number. Wouldn't the tangent, because it's not, yes, it's not increasing rapidly. That means, yeah, we can, it is. Okay, Dave, I understand. Let me just, because even my graph is, but I think it's still, maybe my graph is not really, but it's definitely increasing, but slowly, and it's a little bit, yes, it's not as steep, which, yeah, you said it's getting flattened. That means probably the tangent line at 16, but I think still the tangent line at 9 will be better. Yeah, either way will be good. I think so. But don't, no. We have to, I would say we have to look at the X values. That means since 11, that's what we said, it's closer to 9, we will probably use 9, because we really need to look, we have to be close to that number. Yeah? Because that's actually the point. We have a tangent line, and everything which is close to the tangent line will have almost the same value on the function. Yeah? That means 16, I know, because I completely understand, but 16 is relatively far away from 11. 9 will be closer. Yeah, that's because we still have to think about the X values, not only the shape, but yes, even probably use it. You can even try. Yeah, I will try. After the session, I will compute I will approximate by the tangent line at 9 and the tangent line at 16. Okay, but I think 9 will still be better. I have just, okay. Yeah, but good, yeah, good feeling. Yeah. Okay, 3.96, of course, the 4, it still works. Okay, and I just substitute 3.96. And I kind of, what I did, because I'm trying to compute this without the calculator, that means 3/4, it's 3/4, and 0.96 divided by 4, which this is 0.75, I just used the decimals, and 94 divided by 96 divided by 4, it's 24, because if this will be 100 divided by 4, it's 25. That means it's 0.24. Okay, adding together 1.99. And the real value is a little bit lower because we still have the tangent above. We overestimated, but such a close numbers. Oh, okay, that's the graph. Okay. Yeah, I'm just still thinking about the 9 and 16. Okay. Yeah, that's, we know what we're doing. Oh, find the linearization, different function. Find the linearization of the sine of x at 0. Yeah, the same thing. We just need the tangent line. Please do not be like scared or like intimidated. Oh, what is linearization? Yeah. If you forgot, just the tangent line. Okay. Oh, I have the graph because it's always a little bit confused. We have a little bit of problem. That's sine, and actually the tangent line at sine, I mean at 0, it's a little bit weird because it's kind of like intersecting. And we can still do this because having a curve and the tangent line, we have one common point. But in this case, it's like it's kind of like we intersecting, which normally we will not even say that the tangent line is intersecting because it's like touching. But for this curve is intersecting, but still we satisfying a definition of tangent. It's they have the same direction, and we can see they are almost indistinct. We can't distinguish the difference. Okay, let's find the equation of the blue line. The blue line is, but just in case if somebody will ask you to draw a tangent at 0, yeah, we can see it's intersecting. It's below in the 4th quadrant and it's above in the 2nd quadrant. The 1st quadrant. Okay, we can see it's above. Okay, linearization, 0. Who can tell me the value of the function at 0, value of the derivative at 0? Sine at 0? 0, good. And what's the derivative of sine function? Cosine. And cosine at 0? What is cosine at 0? 1, good. Sine at 0, cosine at 0, and 0, 1. Okay, that means it's really nice. Oh, I should actually not ignoring 0, 1. That's supposed to be 0, and it's just x. Okay, that means this line is simply x. Yeah, y equals to x, or L of x equals to x. This means it's just 1x. That means this is nice because we can say that sine function, sine of x, behaves like x, near to 0, of course, only close to 0. That means we have to be relatively close to 0. Okay, and then we can approximate some values. Instead of taking sine of x, sine of the value, we can just say x. But in this approximation, we have to be careful. We have to use radians. Yeah, that means, for example, even 45, I mean pi over 4, because this will be the real value. Okay, because I just want to, do I have a, oh, okay, I don't have a question with the approximation, but let's try, like let's approximate sine of pi over 4, but we know the value, okay, because that means sine of pi over 4 will be simply pi over 4 Okay, but let's clarify something. That means this is sine of 45 degrees. Do we know the real value? What's the sine of 45? Sine of 45 is, okay, that's 45, and this will be the red value, square root of 2 over 2. That means this is the actual value. Can you use the calculator for me, and can you actually get the decimal? Like, can you divide square root of 2 by 2? Will be 1.4 divided by 2, 0.7, 0.7705, 07, okay, that means 0.707, okay. And now you will say, oh, how this is equal, but we have to think that pi over 4 radians is like we have to get the value. What you can do, you can take, also please use the calculator, pi as a number, as a value, 3.14. 3.14 divided by 4. Can you use the calculator and check? Yeah, that means this will be actually 3.14, because that's we can't use, of course, degrees. Oh, no. Yes, okay. It's okay, 785, but this number, let me use the blue. We did overestimate, but you can see the blue dot. This will be 0.785. The blue dot is definitely higher than the actual value, the red dot, okay? But I wanted to show you what this means, sine of pi over 4 is pi over 4. It is, because sine of 45 is root 2 over 2. You gave me the real value, that's the real value on the left-hand side. And on the right-hand side, I have approximation, and it works. That means we have to remember that this we have to treat as a number, okay, as a real value. Okay. Yeah, that means sine of x behaves like x, yeah, at 0. And this is not really a proof and everything, but I like to say, because do you remember the limit, sine of x over x at 0? What was this limit? Yeah, it's 1. That means it's not really, it's a little bit different reasoning, but actually sine of x at 0 behaves like x. X over x is 1. Yeah, do you like this? Yeah, it's nice. Yeah, nice proof. Of course, we have a little bit different proof for this limit, but yeah, we can think, oh, sine of x behaves like x at 0, yeah, close to 0. X over x is 1. Yeah, really nice proof. Okay. Oh, I have this function. This is funny function because we have lots of calculations, but let's do this one. And I think I have one more. Okay, and we will, yeah, that means I will not talk about the differentials, but I will put the short video for you and you can check tomorrow morning, okay? Yeah, it's something similar, but let's stick with the linearization, because that's the important part. Okay, find the linearization for function x to the power of 3 over 4 at 16. That means this one, of course, this question is testing your linearization and the new concept, but also a little bit of algebra. Okay, I will start with this equation, f of a plus f prime at a, x minus a, and a is 16. And now, who can tell me the value of the function at 16? Did I calculate this? 16 to the power of 3 over 4. This rational exponent, the denominator, is telling me that this is the 4th root, right? That means what is the, yes, 4th root of 16 is 2. 2 cubed is 8. John gave us the number, 8. That's when you can see it's a little bit algebra, but it's still not bad. Okay, that's what we do have. Now, that means we know this number is 8. Now, the derivative. Derivative of x to the power of 3 over 4 will be 3 over 4 x to the negative 1/4. and I can rewrite as a fourth root in the denominator because it's negative. And can you substitute 16 now? Fourth root of 16 times 4 and 3 on the top. That means what will be the value? 3 over 8. 3 over 8. Okay, that means we definitely need this number and we need this number. Good. Please make sure that you know this calculation, okay? Okay, that means this is the linearization. That means I probably, yes, I did distribute. That means I do have a nice slope intercept form, mx plus b, but we remember that form, it's also helpful because now I can put some values instead of x and I know how far away I'm going from 16. Yeah? If I ask you to evaluate at 18, yeah? 18 minus 16 is 2. Will be easy to calculate. Okay? That means make sure that even if I ask for this form, you will see on the option, remember to use this one in case of the approximation. Okay, we made this question. Yeah, and we of course using to approximate. Okay, let's, near to 16. And you can see from that form, we will not really tell that is the tangent line at 16. From that form, we nicely see. Okay, let's do this question as a last question because it's interesting. It's similar that we did for square root of like 7, right? Yeah. Use the linear approximation to estimate 2.001 to the power of 5. Okay, that means we have to find linearization. But what do you think? What is missing in this question? Like, is this like instruction a little bit limited? What is missing? A value, okay, but A, that means Kevin said A, good. But what do you think? This question asks for the approximation, and of course, the number is funny, 2.001. That means what is the nicer number which is close to this one? Which that will be my A value. The nice, okay, 1, but maybe just 2. Yeah, even closer. I know, John, of course, 1, because then the calculation will be so, okay. But I think we can stick with 2 because 2 we will have better approximation. 2, okay. That means the A value, the closest integer, the closest nicer number, because it's to the power of 5, that means it doesn't matter if it's 1 or I mean, it's not a specific like number that goes well like square root of 4, square root of 9. This one we can like take any nice number to the power of 5, but not this. That means, let's say this is the closest nice number, A. But also what is missing? Can you tell me what is missing? A number, and the main thing is a function. Yeah, the function, yes. Justin, Jack, probably the function. That's looking at this quantity, 2 to the power, 2.001 to the power of 5. What do you think? What will be the formula of the function? Because this is kind of telling me, yeah, this is my quantity. Yes, this is x to the power of 5. Okay, that's mean I did type this. I didn't cross, I just put x. That means I can tell you in this type of question, this is probably the most like challenge, the first few steps. Because based on the number, we have to figure out what is the function and what is the A value. Okay? And now, just the work, just the job that we have to do. We have the equation. Everybody knows the equation after today's session. But if you will forget that form, just the tangent line. Now the number is 2. And who can tell me the value of the function at 2 and value of the derivative at 2? Value of the function is 2 to the power of 5 is 32. Really good. What about f prime? What's the derivative of this function? X to the power of 5 is, yes, 5x to the power of 4. And when we substitute, oh, not a, 2. 2 will give me 5 times 16. It is 80. Yeah. Oh, it is 80. John said 160, but okay, Josh said, well, okay. 32 and 80. Okay, and that we can see this is the nice form. Okay, because now we will see the difference. This is just a nice mx plus b form. Let me just put, this was 32 and this is 80. Okay, and now we can take we can take function x to the power of 5, and instead of taking number to the power of 5, I can just I have to just take the number and multiply by 80 and subtract 128. Yeah? But only near to x 2. Yeah? Because we can nicely see from that form, only near to 2. And actually I'm using that form. Can you see I'm using to approximate that form? Because now I can only multiply 80 by 0.001, which will be we can move 1 to 3 decimal places and add to the 32. Yeah. But can you imagine taking this number 2.001 to the power of 5? 2.001 times 2.001 times 2, that will be too long. And now we have a nice approximation. Do you think did we overestimate or underestimate? I don't know if we can nicely guess this. Over. Okay, what we can do, function x to the power of 5 looks almost the same like x to the power of 3, a little bit slimmer. And now when I will draw at 2 a tangent line, that means the tangent line actually is below. That means we have the value. This is the value on the tangent line. Yeah, it's close to the blue dot, close to the red dot, to the actual. Yeah, that we can see the red dot is the blue dot is below. That means we underestimated. Yeah, but of course this is just additional question. Okay, I think we can finish, but let me just check one. This is nice question. You can check the solution, okay? Because this is the same type of question. Oh, don't worry for this one. You can check, but it's a little bit crazy. That's what I have. But let's see, let's just finish the session with this, because you can see I can ask you this way. The question, the solution that we did this question, but was actually quite easy, a little bit easier because we have the function. But can you see this like how the way that I ask? Use the linearization to estimate square root of 7. That means, as I said, then the most challenging job will be to figure out what is the a value and what is actually the formula for the function. And can we just make sure that we know that the function will be square root of x? Yes, okay. Square root of x. Always like the number that I'm asking to approximate, to estimate, will give you the formula, square root of 7, square root of x. And the a value, what is the a value? Oh, no, 7. Yes, the a must be the the closest number, of course, but the nicest number in this environment, that means it will be 9. Because then we can nicely get the equation of the tangent line. Square root of 9, derivative at 9, no problem. And then substitute 7. Okay, that means this, these settings, and the rest of them, you can do it. Okay, that means this is everything for the linearization. We have another part of this section, but it's a little bit shorter, talks about almost the same thing, but it's a little bit different, like angle, looking at these numbers, and also a little bit different terminology. But maybe I need like 15-20 minutes. That means that I will provide the video for you, okay? Check tomorrow morning the video about the differentials. Okay, that's everything for today. And thank you, for staying with me. Thank you for computing, and thank you for using the calculator. But was just the teaching, the teaching, like we don't need the calculators. You can use the tangent line to approximate everything. Thank you. Thank you.